All right, we're going to move on to our next lesson. So we finished dealing with logarithms, trigonometry. So our last topic for this derivative unit is we're going to look at exponents and logs. So today we're going to actually backtrack and learn a little bit something new about exponents and logs, and that'll help us able to solve regular exponent and log questions in the next lesson. So today what we're going to look at is the e number and log base e. So quickly, just remember that a log and an exponent are inverses of each other, or the diagonal reflections. So in Math 30, we would do often log a base 2. So that means if our exponent equation was 2 to the x, the inverse then was log base 2. So those, and it doesn't matter whether it's base 2 or base 5 or base 10 or whatever, but the ones that we're going to learn about today is we're going to look at what happens if the base number is e, and then what happens if the base of the log number is also e. So that's the two scenarios we're going to figure out today, and we'll be able to do those derivatives, and then from there that'll help us solve the other types. So for all of our possible base numbers, the most convenient and probably the easiest is if we use the base number e. It's named after a German mathematician, and his name was Leonhard Euler. It's pronounced Euler, not Euler. And Euler's number, he figured out, is approximately 2.718. It's sort of like pi. It's just a repeating decimal. It's irrational. Doesn't really have any kind of fraction or anything like it. But it was sort of first derived from a financial perspective. There's lots of uses of it, but I'll just kind of show you if we did an infinite limit of 1 plus 1 over n to the power of n, that would give us Euler's number. So that was sort of the first application of it, and it comes from compound interest. So if you put $1 in the bank and you had 100% interest, at the end of the year you'd have $2. You'd get 100% of your money back. If you had $1 and you were getting 100% interest, but you were getting interest quarterly or monthly or daily or weekly, those compounding would get bigger and bigger. And the biggest, if we basically did compounding every second, it would max out at 2.718. So they kind of figured it out from a financial or compounding interest perspective. And Euler took that further, and he looked at it from a graphing perspective, calculating slopes and doing derivatives, calculated area under the curve, and it's sort of like an optimal number that shows up in a lot of places. A lot of things in biology tend to follow a pattern of exponential growth based on the number e. So it does happen quite a bit. So what we're going to look at today is if you took this formula and we tried to solve a limit question. So just like we did with sines, remember when we had something like the limit as x approaches 0 of sine x over x, we couldn't prove that any other way other than just graphing, or we use the squeeze theorem or plugging numbers on either side. It works sort of the same for e. We have to sort of have a base limit value for e, and then from there we can use that for other derivatives and stuff. So our formula looks fairly similar. It's almost like the cosine one almost, where you have e to the h minus 1 divided by h, plug in a 0, that would give you 0 over 0. But if we actually put a number on your calculator and test the left and rights, or we look at the graph or whatever, we would see that our limit ends up being 1. So we're not going to prove that formula. We'll just like I said, we kind of do it the same we did for sine or cosine, and it would be good enough. So what we're going to do is we're going to use this limit to help us solve other derivatives. So if we go back to first principles, so if our starting equation was y equals e to the x, our goal is, could we figure out that derivative? So if we plug it into our first principles formula, we would have e to the x plus h minus e to the x divided by h. So that first step is the same as we normally would do. So now our second step is we kind of do the same thing. Remember, if you have x2 times x to the 4, we basically would add those two together to get x to the 6. Oops. So the logic works the same, but we're just kind of working backwards. Okay, so if I give you something like e to the x times h, our e, like if you look at sort of this step, I'm going to kind of work backwards. If I gave you something like e to the 2 plus 4, we could split that part as being those two things multiplied together. So you can see I can change this e to the x plus h into e to the x times e to the h, just using that exponent law. Now what we can do, sort of our next step, would be to common factor out the e to the x. So if we take out e to the x, we get e to the h minus 1 all over e to the h. And that's basically all we need to do, because we can see that on the previous page, our limit as h approaches 0 of e to the h minus 1 over h, that was given to us as being equal to 1. So that means all of this stuff in our formula turns into 1, so our final answer should just be e to the x times 1, which basically means our derivative then is just e to the x. So our final answer is the exact same thing we started with. And that's part of the reasons why this is sort of called a natural number. It's one of the only functions, or probably the only function, where the derivative is the exact same thing as the original. So if you were to graph y equals e to the x, let's just sort of look at it quickly here. It would look just like our normal exponential graphs, except it's be a little steeper than 2 to the x, but a little less steep than 3 to the x, so it's somewhere in between those two. But if we were to actually calculate the tangent slope on any of these locations on this graph, the slope is also determined by the exact same thing. So it's kind of strange that it's the one function whose derivative or whose slope is the same as the original. So what it does is it helps us allow us to solve all kinds of exponent and log questions because of it being the exact same derivative. So now if we know that the derivative of e to the x is also e to the x, we can actually use that to help us figure out log base e. So when we write log base e, the shortcut is we just write it as ln, and that stands for natural log. E is often called the natural number, so the natural log works the same. So often we'll just write it as ln instead of log base e. If you were getting some other log, if it's log base 5, we leave it as log base 5. If it's log base e, we then just say ln x, and that's the English, or the way we pronounce it, like you're mowing your lawn. So ln x times 5, ln x divided by x, those type of things. Okay, so if we wanted to calculate the derivative of log base e or ln x, the simplest thing to do is start with it as y equals ln x. I could also rewrite it as log base e. And now we could do the crisscross formula, right? Just like we did with other logs and exponents. To convert from a log to exponent, we would go e to the y equals x, right? Those are these two things are the exact same thing. So what's nice is we actually change the log to an exponent. Now we can do our regular implicit derivatives. So if our left side is e to the y, the derivative of e to the y would be the exact same thing, but because we have the y, right, we have to do the derivative of y, which is y, or 1, but then we need the dy dx. The other side, we just get 1. So to solve this, our derivative should be 1 over e to the y. And instead of writing it as y, we're just going to do this substitution step. So we're going to write that as 1 over x. So both the derivatives of e to the x and ln x are actually both quite simple. So that's what makes it nice. And that's why we start with these, because now we'll be able to apply this. So what we've just saw is derivative of e to the x equals e to the x. Derivative of ln x is 1 over x. Both of those formulas are on your formula sheet, and you'll have them memorized pretty quickly anyway, because they're both pretty simple. The ones below it here are the same formula, but we kind of use the chain rule again. So remember, if I gave you something like sine x, the derivative was cos x. But if I gave you something like sine of 4x, the first part was do the derivative of sine, which gave us cosine, and we had to multiply by the derivative of the brackets, which in this case was 4. So our final answer was 4 cos 4x. So that chain rule idea of timesing by the derivative of the brackets works the same, except we just do it with ease. So in this case, if our power is something other than an x, we have to times it by the derivative of that exponent. And for logarithms, it also works the same, except think of whatever's after the natural log, think of that as being in brackets, and then it's more like a trig derivative. So you go 1 divided by the brackets, and then times by the derivative of the brackets afterwards. So let's look at a few examples, and you'll get the hang of this fairly quick. So our first example we have here is y equals e to the negative 4x squared. If you want, you can think of the power as being in brackets. That might help you understand the chain rule a little bit better. So the first step is derivative of e stays the same, so everything stays exactly the same. But now we have to times it by the derivative of the brackets, or derivative of the exponent in this case, which would be negative 8x. And then, just like we do before, it's usually a good idea to just bring that extra stuff out front. So it'd be negative 8x times e to the negative 4x squared would be our final answer. If you wanted to put that in brackets, you can. If you want to separate the 8x from the e with a dot, that's fine. Some people would put brackets around it. It's totally up to you. That doesn't really matter too much on how you write that. Everything's being multiplied. So if you look at my answer in the bottom corner, we have negative 8 times x times e to the negative 4x squared. Alright, here's another one where we're mixing exponents and trig together, and it works fine. We just have to do the appropriate rules for each. So the first thing you can see is we have e to the negative 3x times cos 2x. So again, you could think of these as being brackets if you want for both the power and the trig part. But the more important thing is with this one is we have product rule. We have two things being multiplied. So let's start with that. So let's start with f being e to the negative 3x. So that derivative would be, keep it the same, times it by the derivative of the top, which would be negative 3. So let's write that as negative 3 e to the negative 3x. And then do the same thing for the second part. If g is cos 2x, derivative of that is negative sine 2x times the derivative of the inside, which would be 2. So let's simplify that as negative 2 sine 2x. And again, if you want brackets on these, you can put them. If you'd rather not, that doesn't really matter. Okay, so now we should be good to do our product rule. So let's multiply those two. So that gives us negative 3 e to the negative 3x times cos 2x. And then the other two multiply, but they're added, but this one's already subtracted, so I'll just leave it as minus 2. Let's put the e first, e to the negative 3x times sine 2x. And you can see that matches my answer that I have in the bottom corner, so we could stop there if we want. Now that I look at it, we could probably simplify it a little bit. We could pull out e to the negative 3x as a common factor if we want. So that would give us negative 3 cos 2x minus 2 sine 2x. And if that was an identity, we could maybe put it together, but in this case, I think that would be plenty. Here's another one. You can see it has a regular mixed with a log. So again, watch for things being multiplied, and that's exactly what we got going on here. We have f times g again. So if f is x, derivative of x is just 1. If g is ln x, derivative of that is 1 over x. So that makes it pretty simple. Do our product rule once again. So we'd have x times 1 over x plus 1 times ln x. And you can see the x divided by x would cancel, so that should just simplify to 1 plus ln x would be our final derivative for that equation. So works pretty good when you have 1 over x, because a lot of times those kind of things will cancel out. Okay, here's another natural log one. So again, remember the rules for natural logs is the derivative of ln becomes 1 over, so we keep everything the same inside the brackets. Just go 1 over all of that term. Now we got to multiply by the derivative of the brackets, which would be 2x plus 2. And we could leave our answer written like that if we want. Let's just put it together as one big fraction. Or you can see in the bottom corner, I just factored out a 2 on the top, so 2 times x plus 1. Both of those answers would be good. And here's another one. We have logs and trig mixed together. But again, just follow it outside in like we do with normal chain rule. So derivative of ln is 1 over, so we'd have 1 over cos. Now the derivative of the brackets is, derivative of cos is negative sine. So that should simplify to negative sine divided by cos. And we can use the trig identity. Sine divided by cos is the same thing as tan. And that is all. So you can see derivative of e to the x is easy. We just keep it the same. Derivative of ln x is almost as easy. It's 1 over. So if we remember those two key things, that'll help us solve any of these kind of e or log questions. And then our next lesson we'll apply this to doing base values that aren't e. And then it's slightly more complicated, but the concept is roughly the same. Okay, we'll stop there and move on next time.